Welcome to the second video in the Dynamic Systems and Control class. In this class, we'll be going over flow and effort. These are going to be two sources that we're going to be utilizing within our bond graph system. From the earlier video, you should recognize that we have three major components in a translational system: mass, we're also going to have a spring, we're also going to have a damper. We're going to utilize these and two new concepts called sources of effort and sources of flow to help solve problems. Now, we're going to be creating a bond graph utilizing these components in an example that we've been given. It's a mass spring damper system. Let's take a wall here. It's fixed. We're going to add a mass to the right side of the wall. And we're going to add a spring that's connecting the mass and the wall together. They're just connected right there. We're also going to add a damper in between the system, right here. And let's hypothetically say that there's a force that's tugging on this system right here. This is the mass spring damper system. We have all three components utilized here: mass, spring, damper. And this force is going to be an example of effort. An example of flow is a velocity relative to a plane. So the velocity that we may be interested in may be relative to this fixed plane right here. But we weren't given a fixed velocity, we were given a force that's being applied to this system. So, how do we consider this system? Well, there are two other concepts that we need to know. Common force is denoted by a 0 in a bond graph, and we'll go over what a bond graph is. And common velocity in the translational system is also known as a 1. Effectively, all the components that are connected to this particular system with some arrows have a common velocity, and then if they're connected to a 0, then they all have a common force. Well, is this a common force or a common velocity problem? Or is it a combination of both? How do we know? Well, we know that we are given a force right here. We have a mass, and we know that mass is not going to deform, because if it was, then we'd be modeling that in a spring, and we'd be modeling that with a damper. But we also have both, so we know that this is a rigid body, right? We also know that this spring right here and this damper move at the exact same rate. If you take this to be your 0 point, and you take this to be your x1, you know that they're both displaced by the same amount in one dimension. You also know the mass is displaced by x1, and therefore you can actually squash this mass down into this representation, which may be easier to understand. We're going to say that the mass is a single line. I know this is not true, but it helps us see in one dimension that however much the mass gets displaced by, the other two components get displaced by the same amount. So say that we start at x1, yeah? And then we displace by a certain amount, and the spring gets pulled to this location, and the damper gets pulled to this location. The mass moves to this location. We'll call that x2. Well, all the components here have been moved by x2 minus x1, right? And this is just the one-dimensional coordinate space that I have right here. x2 minus x1 is representative of that change right there. So we're going to treat this problem as a common velocity problem, because even though they're displaced by the same amount, they're also displaced by the same velocity. Why is that? Well, effectively, velocity is equal to x d over dt. That's a derivative. So the derivative of displacement, whatever displacement is going to be velocity. And since time changes for the same rate for the spring, for the damper, and for the mass, since time is moving the same for all components, we can also say that this is a common velocity problem. So we're going to put a 1 right here. We're making a bond graph right now. A bond graph is a representation of a system using symbols. So we're going to use a symbol of 1 to denote common velocity, because that's a common velocity problem. We're going to have a source of effort. There's an arrow that's going to be going into this system. It's going to be a source of effort, which is just going to be that force right here. We denoted it by an F. I'm going to put an F right on top, right there. Next, this force is being translated into other components. So this mass is experiencing that force. The spring and the damper are experiencing this force as well. So we're going to have a line that's going out, and I'm going to erase this title bond graph, but just remember it's a bond graph. Then we're going to have arrows that are coming out right here, right? See, and then we're going to say This is going to be an I, which is an inductive component, which is representative of the mass. Then we're going to have a representation of the spring, which is a spring is going to be a capacitor, right? And that capacitor is going to be the inverse of the spring coefficient, 1 over K. And K is the spring coefficient. When you're trying to measure the force of a spring, you do the K times the displacement of that spring. It's going to be 1 over K, and then the resistor is going to be the damper, and the damper is going to be denoted by B, which is the dampening coefficient. And in the next video, we're going to take this graph that we've created, take a look at this and see how I got to this point. We're going to take a look at this graph and we're going to create some equations that model different things we might be looking for in this particular system. So, thanks for watching. Please subscribe. If you have any questions, comment down below and try to help you out.